Well, good morning. So, today we will continue the discussion since last week we have the discussion for revised version for TCP congestion control, QB. Right now we will have BBR. Alright, so let us continue. So for bottleneck link here, first of all, if we increase the sending rate, can we have the expected increase throughput? Here it says no. And second one, if we increase the sending rate, actually we have the congestion later. Therefore, we enlarge RTT. Alright, so currently based on the bottleneck link or bottleneck bandwidth, we have the two observations. We cannot increase the throughput and we will prolong the RTT. Therefore, we will have the calculation for reference. You see, we expect to keep the end-to-end pipe that says the link just full, and why just full? Because we don't want to have the congestion, and so that we can avoid the congested link. So the way to do here, we want to keep. Alright, we want to keep the pipe just full enough. That says near the congestion, but do not have the congestion. Alright. So we want to have this approach. And later actually we have a shorthand. It is called BBR. Bottleneck bandwidth based on RTT. And RTT actually is the delay based approach. So later we will have a shorthand we call BBR. So this approach actually we will have RTT. We expect to have the high throughput. So initially RTT should be small. Well, therefore, assume we have the minimum observed RTT. And this one actually it will be the for the uncongested path. And so that we can have the uncongested throughput estimate. How to estimate if the current window is CWND. Right? Based on this ratio, then we can have the rough throughput. But the throughput is not the goal for us. Actually, we expect to have a bit higher, or maybe higher throughput, larger than this minimum throughput. Well, then we have the two actions, action 1 and action 2. Alright, action 1, we have the throughput very close to the uncongested throughput. What that means? This is an uncongested path, and it's the initial throughput. Close to that one that says uncongested. So here we think it's uncongested. Alright, so first one, near the uncongested throughput, therefore we should increase the window. So this is the first observation. And the second observation, far below the throughput. We just check far below. Far below the throughput, then we need to, because far below, okay, maybe we have the estimated throughput, but right now maybe it's too high. Maybe this is a higher one. So too high, therefore we cause the far below throughput. Then we need to decrease. So this one maybe you don't think it's intuition because, oh okay, this is the current uncongested throughput. Far below we should increase the window. But currently no, because we have a congestion. Far below that says it's abnormal. Abnormal says we should have congestion. Congestion, then we should decrease CWND. Alright. So BBR follow the two actions. If we have the asthmatic one close to the asthmatic one, that says near the maybe uncongested level. However, far below, then we need to increase. And as for the others, actually, it doesn't mean we need to tap one of the two actions. Therefore, based on BBR, we have the two possible cases. Action 1, increase. Action 2, decrease the congestion window. Well, of course, we should have the major throughput. How to have the major throughput? This one. We can pass on the current RTT, and the current bytes we send, actually it is related to the current window size. Therefore, we can have the major throughput. Based on the major throughput, then you can apply to these major throughput and major throughput so that you can have the possible comparison. Well, so this is the description for BBR, or it is called the delay-based TCP congestion control. Well, that one we think it can keep delay low, and also the something like the buffer or maybe the possible congestion level near full. Alright, so this is approach for delay-based TCP congestion control, or the BBR. And actually it's BBR. So BBR deployed on Google's backbone network. So Google employed this approach. Well, up to now we already have some possible variants of TCP congestion control. So first of all, we have the classic one, TCP, classic one. And later we have a qubit. And finally we have a BBR. So we have two variants, qubit and BBR. Compared to the original version we call the TCP classic. Well, so this is the congestion control employed by TCP. And beyond that one, we still have the explicit notification about congestion. So we have the following way to modify the original version of TCP. Remember, originally the congestion control taken by the original TCP, we think it is not the network assisted, right? And we have the enhanced version. We pass on network assisted. Therefore, TCP, it is the end-to-end approach congestion control, or the network assisted congestion control. In fact, we have both versions for TCP. Previously, we assumed based on the end-to-end observation. So we have the previous classic one to have the congestion window control. And right now, we have the network assisted one. The network assisted one is back to have notification. Alright, to have a notification. To have the notification, it's easy because we can set the possible fields, and so that we can have the indication of notification. So we reserve 2 bits in IP header. We have a field. It is called TOS field. And we can map by the router so that we have the network assisted action. And the 2 bits can indicate congestion or not. So here, we can have the bit ECN, explicit congestion notification. And feedback, we can have ECE, the feedback for the acknowledgement. So we can have the possible approach 1 and 2. For the router, we can enable, and so that we can have congestion notification. And for the app, we can have ECE to have the notification. And so that we can have the explicit congestion notification. Well, so this is the network assisted congestion control to let the two-end system know congestion or not. So talking about notification, TCP applied the network assisted approach. However, for the previous discussion about the congestion control, we're based on the end-to-end approach. Well, so right now, let me have the attendant check in first. 2 minutes as usual. And in fact, today it should be 10 week. So if you can change your group member, sure, feel free. Now actually I've seen some of students online, so I think maybe time almost okay. And till the end of the timer. So let me get back to the slides. Discussion for TCP congestion control. Well, so think about this. We have the classic one. We have a qubit. We have a BBR. So we have two versions of TCP congestion control. And after that one, we didn't know about notification, TCP congestion notification. We can pass on the network assisted approach. Therefore, if we have a question, TCP congestion control employ simply the end-to-end approach, correct or not correct? It's not correct because about notification, it is the network assisted approach. However, if we think about, or we didn't have the question explicitly, TCP congestion control regarding the congestion window adaptation. It is the network assisted approach. Is it correct? No, right? Only notification. Congestion window size control. In fact, it is the end-to-end approach. All right, so I then have the remark about end-to-end approach to control the congestion window for TCP, and also network assisted approach to send the explicit notification of congestion if yes, so that we need to ask the router to notify. Well, next one. In the past, we didn't have the discussion, maybe the short discussion. TCP will share the bandwidth. Therefore, TCP should be fail sharing approach. However, is it true? So right now, we didn't have the simple scenario, this one. Thinking about connection 1 and 2, share the capacity R. So should we have the equal share? So that'll check. If it is an equal share, then the goal for us actually, if we have k simultaneous TCP sections, then we will share the same bandwidth. Therefore, R over K is the goal for TCP. And right now we want to check, is it true? Therefore, we have a question. Is it TCP really fail? Of course, the goal for us, it should be yes. But how to check or how to demonstrate TCP will achieve the file sharing? Therefore, we already have the previous two competing TCP section. Why competing section? Because each one wants to have more bandwidth. Therefore, it's possible to have the competition between the two TCP sections. And first of all, remember we have AIMD. And currently assume AI increase linearly. And the MD, we have the congestion window. So, linear. This one, assume we have a connection 1. Increase linearly. And here, assume we have a congestion. Right? So, congestion, then we need to have. And this is a way to have. Because currently, it's, for example, we have R prime. And here, it should be R prime over 2. About the current way to have. Can you understand the current illustration? Increase linearly, right? And then half. So here we have half of the congestion window size. About the current way to jump to the current position. It should be okay, right? If that is okay, then we repeat the current procedure. Repeat the current procedure says AIMD, AIMD, AIMD. So, next one, AI again. And we have a congestion. So, MD, AI, MD, AI, MD. So, while we have the expected curve, this one, this is the expected curve we want to approach by connection 1. And likewise, you can something like exchange the role of connection 1 and 2 to observe connection 2. And connection 2 will approach the curve as well. So, based on the simple example, to have two competing TCP sections, actually for each connection or for each section, they will achieve the curve here. For the curve, what's the capacity share by connection 1? It's R over 2. And likewise for connection 2, it's R over 2, shared by connection 2. Therefore, for two competing TCP sections, in fact, based on AIMD and based on the current observation, when we reach the stable situation, TCP will share bandwidth equally. So, finally, we have this observation. Is it TCP? Oh, sorry. Is TCP fail? Or is it fail for TCP connection? The answer is yes. Alright, the answer is yes. And based on this observation, we can extend to the general situation to have more competing sections. And so that yes, we can have K section, so that the bandwidth should be R over K. Alright, of course, you may have a question. Exact share exactly? Initially, no, but finally, if we have the stable one, then yes. And also think about if we have the complicated network scenario. So we still have the exact sharing. Actually, this is the goal for the TCP operation. And eventually, we should have the file sharing. But of course, we will allow a bit fluctuation. So that one is possible. And finally, if we simply talk about, oh, all right, I already have a capacity R and already have a K section simultaneously, and what's the bandwidth shared by each TCP connection? For us, actually, we just use the final outcome to share the bandwidth. So we have R over K. Well, so after now, we already have the way to observe TCP should be fair. Even you don't think it's the ideally fair, but actually, yes, we will have the fair sharing by each TCP connection. And talking about TCP, and right now we want to make sure TCP actually should be fair. And how about UDP? UDP, no. It's not fair for UDP. And right now, if we want to apply multimedia applications, and why? Why we don't want to use TCP? Instead, we want to employ UDP. One reason should be TCP share the bandwidth fairly. So sometimes multimedia want to have more bandwidth. So it is not okay to use TCP simply. Therefore, we want to use UDP, and so that for the multimedia application, they can have the degree of freedom to have the possible bandwidth. Here I mentioned possible bandwidth. If we can have more, of course, we expect to have higher bandwidth, or maybe no, so we expect to have the degree of freedom. That degree of freedom, you should use TCP to achieve it. Alright, so this is the possible choice if you don't want to use the fairness of TCP, then you should use UDP. And further, yes, TCP can share bandwidth fairly, but for the application, sometimes we want to indeed to use TCP and to have a bit higher bandwidth. So how to achieve that one? Therefore, we can have this. For one application, you can employ multiple parallel connections, parallel TCP connection. Someone like, oh, we can form the group. My group, we have 99 members. Your group, just one member there. So, of course, my group can earn more bandwidth. So we use this concept, and here we already have routers, and of course we have link bandwidth is R, and currently we have 9 existing connections, and we want to have one app using one TCP connection, and so that how to have the rate? It should be 1 plus 9, so we have 10. So for the new application, actually it should be R over 10 because we just have a single connection. However, how about if we have a new application employing 11 parallel connection? So 11 plus 9 we have 20, and 11 over 20 multiply R, and here we have the approximate bandwidth. It's a half. Exactly, it should be 11 over 20. Well, so this way we can employ TCP parallel connection. Still, you can have more bandwidth, but you need to have a parallel connection, multiple parallel connections, so that you can achieve more or high bandwidth you shared by using the TCP connection, multiple TCP connections. Well, so for failures, actually, we have the two different angles to observe. First of all, if you don't like the TCP fairness, yes, you can employ UDP, for example, multimedia. Usually we use UDP. And if indeed you still want to use TCP, however, you want to have the higher bandwidth, then you need to have the multiple connections, multiple parallel connections. Then it's still okay for you to have the different bandwidth sharing, because you can have the aggregation of bandwidth. Well, so this is the current discussion. And actually, from TCP congestion control to the current point, that you have 2 minutes to have the discussion. Discuss with your neighbors for 2 minutes. So feel free to discuss. And you can move. Sure, you can move. And feel free to change the group, because this way we allow you to change. And actually we force you to change. So about the current discussion, I use a really simple question. Even sometimes it's a nonsense question. Any questions? All right, should be no. Let me move on to the next one. Well, next one, we will talk about the evolution of transport layer. That says someone like TCP or UDP or the others. So we better have the evolution of transport layer functionality. Of course, initially we have, because of evolution, so we have TCP, UDP. And currently we have maybe more than this. At least more than 40 years we use TCP, UDP. And actually we expect more. And so that we will have the different flavors of TCP developed. So we change it. And of course we can have the password explanation. And right now we have a different scenario here. And so that we will have the challenges. And first one, how about long flat pipe? That is the wide area. And solid long flat. Therefore, we have many packets. And solid many packets possibly will bring the packet losses. And packet losses then possibly here he mentioned shuts down the pipe. So this is the first scenario. And you can check the others. Actually, we may have many challenges. And of course, because of these challenges, and then we expect to have the evolution of the TCP of the other protocols. So, we want to move transport layer functions. And if current transport layer function, for example, TCP, UDP, specifically here we talk about TCP. If TCP we have many challenges, can you finish that one and so that we have the beta version? Of course, if no, then we need to change. How to change? Currently, we have the assumption TCP and UDP only. If TCP cannot achieve the functionality, and then what to do? We will think, all right, we want to do something by the app layer. So we choose UDP and try to move the function to the app layer. So you see, moving transport layer function to app layer. And on top of UDP. And yes, we pass on this one so that we have the example HTTP3. HTTP3 previously, yes, we pass on TCP before the current version 3. However, for the previous version 1 and 2, and however for the current version 3, then we have a new version. The new version passes on UDP instead. And the current version we have a name. Follow the current name we call Quick. It's still called Quick. So yes, TCP, if you don't like it, you can use UDP. And however, if you use UDP for the application layer should take the responsibility for the remaining functions if the current UDP cannot provide. So why we call Quick UDP internet connection? So we have initials QUIC. All right, QUIC. So we have the version. In shorthand, it's Quick. Yes, it's Quick because it is the Quick UDP internet connections. Well, so for this one, actually, we still expect the better performance for the app layer. So here, the performance of HTTP, it says beta. All right, if we follow the description, it's beta. And so then, here we have many Google servers employ Quick. Well, and so how to do? Here, this is a version for Quick. Previously, if we have TCP, then TCP will work with the TLS, something like the authentication scheme or the security level, and finally it's the HTTP. So this is the original version using TCP. Alright, so based on this version, it's HTTP version 2 over TCP. And the current solution, we have a Quick. Quick somehow like we don't want to use TCP, instead we use UDP. And we have the function of TLS, also part of function of HTTP version 2. So that you can make HTTP version 2 slim. And therefore you can have the new version Quick. And HTTP version 2 above Quick. And Quick above UDP. And Therefore, we can have the combination HTTP version 2 working with Quick. And this version we have a new version, HTTP version 3. And this version then we abandon some functions of TCP. Instead, we have the function taken by the app layer itself. Alright, because previously we have a TCP UDP. If you don't like TCP, and then what to do? Sure, the only choice should be UDP. If you got some UDP, then you need to implement some function by the app layer. So this is the current idea by the app HTTP version 3. Alright, so this is the first class talking about BBR to the conversion quick. And later we will continue. So, before we tackle rest, let me make sure. Any questions? If no, later we will continue this quick and to the next one. And tackle rest.